said last day, the next few lessons, the rest of this chapter, are really important. If you're going to be successful in calculus, you got to figure this stuff out. So we're going to start with 2.2, which is on the power rule. So first, what we're going to do here in the next bunch of days is we're going to come up with a bunch of rules that allow us to find derivatives very quickly. Because I don't know about you, but I'm finding that difference quotient, you know, those long formulas we used to so many times, they're getting a bit tiresome. They take so long. So let's find some faster ways to find derivatives. So the first rule we're going to use is we're going to find the constant rule. And this rule says if f is a constant function, in other words, if f of x equals c, then f prime of x, in other words, the derivative of that function equals, well, let's think of this for a second. Think of any graph of a constant function. I'll put think of graph of a constant function. A constant function is like y equals 4 or y equals -2, right? So what does that always look like? It looks like a horizontal line. So for example, this would be an example of a constant function right there. And we're trying to find the derivative. Now, do you remember what the geometric interpretation of a derivative is? It's the slope of the tangent line. Well, what's the slope of the tangent line of this graph right here if it's a horizontal line? The slope of the tangent line is 0. In fact, this will always be the case. I mean, if you think of it, different constant functions, the only thing that's different between y equals 2 and y equals -2 or y equals 0 or y equals 23 or whatever, they're just in different heights, but it's always a horizontal line. And so the tangent line is always going to have a slope of 0. So there you go, your first rule. If you're taking the derivative of a constant, the answer is just going to be 0. This is one way we write it, f prime of x equals 0. The other way you could write it is d dx of c, where c is a constant, is 0. So here's the two fastest examples of all time. If f of x equals -9.2, then f prime of x must equal what? So what we're doing is we're taking the derivative of this. This is just a constant function, which means it equals 0. If we have y equals 23 over 879, boy, that's some really complicated decimal amount if I was to divide it. But who cares how much it is? It's just a constant amount. So y prime, the derivative, remember these are the two most common ways of designating or denoting derivative, f prime of x and y prime. And so the y prime, the derivative of this is 0 because it's just a constant. Okay, easy, but not the most useful. I mean, we do use it a lot actually, but it's so easy. Let's go to something that's a little bit more difficult. The power rule. This is really important. So this says if the function is equal to x raised to the nth power, where n is any real number, so it could be, you know, x to the 3, x to the 4, x to the -2, whatever, then f prime of x equals, in other words, what's the derivative equal? Or d dx of x to the n, in other words, what's the derivative equal of that same thing? Okay, well, to do this, let's figure out some patterns here. Let's first of all start with a very simple function, f of x equals x. And let's figure out the derivative of that. So in other words, we're going to figure out f prime of x by using the difference quotient, specifically this difference quotient right here. So in order to do that, we would do f of x plus h. In other words, we plug x plus h in here and just get x plus h. And then we would subtract f of x, which is just x, and we divide the whole thing by h. And the x's would cancel, so you'd get h over h, and those would cancel, so you'd just be left with 1. So f prime of x in this case equals 1. Okay, good. Let's do something a little more difficult. Let's do f of x is equal to x squared. So if we use that same formula again, the difference quotient, we would first of all plug x plus h in here. We get x plus h all squared. And then we would subtract the actual function, which is x squared, and we would divide it all by h. And of course we have the limit, but I just don't have room to write it. So we have x squared plus 2hx plus h squared minus x squared all over h. We can cancel this and this. We can factor out an h, so we have 2x plus h over h. The h's cancel, and remember our limit is as h approaches 0. So we plug 0 in here, all you get is 2x. So f prime of x in this case is 2x. Okay, one more. I'm not actually going to do the whole thing. Let's say that f of x was x cubed. Okay, we'll probably do this in class, but just to speed things up a little bit, I will tell you that by doing the same thing that we did here, by plugging x plus h cubed and then minus x cubed all over h, that's what we'd have to do to get the derivative, and if you do that, you get 3x squared. Okay, time to put on your thinking caps. When we had x here as our function, we ended up with 1 as our derivative. When we had x squared, we ended up with 2x. When we had x cubed, we ended up with 3x squared. So can you figure out what's going on every single time to get the derivative? Okay, let's take a look at this coefficient out front. Where is that coming from if you look at the original one? 3, 3, 2, 2. 1, right? There's a 1 right there and 1 there. So that's where the coefficient comes from. You just take it from the exponent in the function. Now, where's this x squared or x? Where's that coming from? X cubed, and then it went x squared, and it went to x1, x1, and it went to x0. Oh, in the derivative, it's always 1 less. So this is it. This is the power rule. If what we're starting with is x to the n, all you do is you take that n and you move it out front. So you're going to have n, and then it's going to be x again, but now it's not going to be raised to the n power, it's going to be raised to the n minus 1. Does that make sense? Let me show you again. This 1 here, we move out front, that's where the 1 is, and this x to the 1 becomes x to the 0. X squared. 2 comes out front, there it is, and x squared becomes x to the 1. 3 here, 3 moves out front, x cubed becomes x squared. Can you believe it? We just have to do that instead of doing all this with the difference quotient. This is a beautiful, beautiful thing. This will be exactly the same. It's just a different way of writing the same thing. So we get the same answer. All right, let's answer some of these. Y equals x to the 100th power. So what does y prime equal? Okay, just use the power rule. Take the exponent, put it out front, rewrite the x. 100 drops down to 99. Now, can you imagine how hard this would have been to do if we'd used the difference quotient? You would literally have had to have done x plus h to the 100th power minus x to the 100th all divided by h. What part of that is really hard? This part right here. Who wants to raise x plus h to the 100th power? That's multiplying x plus h times itself 100 times. No, we do not want to do that. So the power rule is definitely a wonderful, wonderful thing. Okay, often when you use the power rule, you want to rewrite things before you actually use the power rule. So right now we have f of x equals 1 over x cubed. Doesn't exactly look like the form we're looking for here, but how can we make it that form? So this is not the derivative, this is just rewriting the function. Why don't we rewrite that function as x to the negative 3, right? X to the negative 3 is the same as 1 over x cubed. Now it's in the form we want, we can just use the power rule. So f of x, we're going to write the derivative, which is f prime of x. How do we do it? We take the exponent and move it out front. So we have negative 3 times x. This negative 3, the exponent drops 1 lower. What's 1 lower than negative 3? Negative 4. Now, a pretty common rule, I suppose, is we don't like having negative exponents in our answer. So this negative 3 is a constant, but x to the negative 4 means it's a flipping negative, right? It's going to flip into the denominator, and it's going to be x to the 4th power. So that would be our best answer right there. Okay, here's another question that you want to rewrite to get it in the correct order, correct form, sorry. So I'm not writing the derivative, I'm just rewriting the function. The square root of x is the same as x to the what? To the 1/2. Now it looks a little more complicated, but you just follow the same rule. In order to get the derivative, we take the exponent and we move it out front. So that'll be 1/2. Then we write the x, and then we drop this by 1. What's 1/2 take away 1? 1/2 take away 1 is negative 1/2. Okay, and then if we simplify this, what we have is, on the top, all we would have is a 1. On the bottom, we have a 2. This negative 1/2, that means the x flipping into the denominator, so it's x to the 1/2. I'll do it in 2 steps. And then I can do even another step, that equals 1 over 2 x to the 1/2. Well, x to the 1/2 is the opposite of what we did here. It equals square root of x. This is an extremely common derivative that you'll be taking this course hundreds of times probably, when you take the derivative of square root of x and you end up with this right here, 1 over 2 root x. A lot of people just memorize it, that whenever you take the derivative of root x you get this. I'll be honest, I have a horrible memory, so I tend not to memorize it. I just very quickly do this. It doesn't, once you've done this a bunch of times, it takes like a few seconds to go from here to here. You'll get there, don't worry. Okay, one more of this type. Now this is definitely a different type when you first look at it, because you have an x and then another x with square root here. We'd like it to have just that single x, right? Just a single x and then a single exponent. Can we do that in this case? Yeah, you can actually. Again, we're going to switch the function before we do anything else. We're going to change this to x times, because that's what's happening here, right? X times root x times x, but we're going to make it x to the 1/2, just like we did here. So what we have here is two powers. This one's to the exponent of 1, and we're multiplying them together. What do you do when you multiply powers with the same base? You add the exponents. So we can do x to the 1 plus 1/2. Well, in order to do that, we're going to have to get common denominators. Common denominator is 2, so this would be 2 over 2 plus 1 over 2 equals x to the 3 over 2. I don't know why I've gone this crazy route to get my answer, but this is x to the 3 over 2. Now, this isn't the derivative. This is just writing the function in a different way. Now let's get the derivative. How do we get the derivative? We can use the power rule. We take the exponent, which is 3 over 2, and move it out front. Then we write x, and what do we do to the exponent? We drop it by 1. What's 1 less than 3 over 2? Well, 3 over 2 take away 2 over 2, because that's how much 1 is equal to 1/2. So there's our answer. We could clean it up a little bit. 3 is going to be on the top, 2 is going to be on the bottom, the x is going to be on top, but it's x to the 1/2. Why don't we just write root x, because that's what that means. Now we're going to learn the constant multiple rule. This will just become kind of like common sense for you. You won't have to really worry about the name of this rule or anything. This is very similar to one of the properties we talked about when we were talking about limits. All this is saying, this rule is, if you have a constant times a function and you want to take the derivative of that, you can just move the constant out front. So you can move the c out front, then take the derivative of the function, and then multiply by the constant. So take the derivative of the function, multiply the constant. You can do that. This is the other way you could express the same thing. d dx of c f of x. You can move the c out front and then do d dx of f of x. So that might sound confusing. It's not. You'll see in just a second here. Let's do some of these. So we're going to differentiate. When I say differentiate, it means find the derivative. So we're going to find f prime of x. So what we have here is a constant, -5, and then this function x to the 6. So what I can do is I can just move that -5 out front and then take the derivative. So I'll put d dx to show I'm taking the derivative of x to the 6. Okay, so let's just keep the -5 out there. How are we going to get the derivative of this? Hey, we can use the power rule. How do we do that? We bring the 6 down, keep the x, and 6 drops down to a 5. Now, don't forget we had this -5 out here waiting to multiply. So let's go ahead and multiply. -5 times 6 is -30, and then x to the 5th. Now, I don't expect you, and you're probably not going to, even after this next example maybe, you're probably not going to rewrite it like this. You're just going to go straight from, well, you'll probably go straight from actually this question to the answer. How do you do that? You just bring the 6 down and multiply by whatever constant is there. So I bring the 6 down, oh, there's a -5 there, I better multiply. 6 times -5 is -30. Then drop the exponent down by 1. So, that's the way you'll eventually, or start doing it right away. It's okay with me. But that's the way most people do them to save a lot of time. I'll do one more the long way. So f prime of x, oh, I see that we have a constant here. I move the constant out front. Then I take the derivative of the function that's left. Okay, so I have my 9. Now I take the derivative. I can use the power rule. How do I do that? I bring the 4/3 down, rewrite x. 4/3 drops by 1. Well, 1's the same as 3 over 3, so I'm left with 1 over 3. Now I'm going to multiply. Well, when I multiply here, I can ninja slice, as I say with my grade 8s. You can divide them both by 3, so you get a 3 here, 1 here. So what we have left is 12 x to the 1/3. And you can leave that answer, it's fine. But you do know what 1/3 means when you have an exponent. It means 12 and then the cube root of x. Again, probably what you really would have done is bring the 4/3 down and multiply by 9. Oh, 4/3 times 9 equals, maybe you can do it in your head, you get 12, and then drop this by 1 and you got your answer. Okay, this one here, it looks similar, but you can't just move that 4 out front and treat it like the constant. Do you know why? It is a constant, but here's the thing. It's also being cubed. So what I would do here actually is simplify the function, expand it. So I'd go x cubed and 4 cubed, which is 64. And now you can actually do the same thing we've been doing up here. Now you could put that 64. So this is just still the same function. It's written a different way. Now we're going to find the derivative. So the 64 moves out, but make sure you don't just put 64, because this is 64 in the denominator. So it's 1 over 64, and then take the derivative of x cubed. And away you go. We have 1 over 64 as our constant. Going to use the power rule. 3 comes down. X, 3 drops down to 2. Now we'll simplify if we can. Can I ninja slice 64 and 3? No, there's no simplifying there. So you're done. Let's just put 3 over 64 when you multiply those two things together, and x squared. Or if you want, 3x squared over 64, same thing, no problem. This one's very similar. You can't just move the 2 out front and treat it like a constant. It is a constant, but it's being raised to the 4th power. So again, you should expand this out. Spreading the love, I think I call it. All these silly names I have. Okay, so first thing, I'm not going to find the derivative yet. I'm just going to rewrite this. So I have 2 to the 4th power. Well, that's 16. And I have t squared to the 4th power. Power raised to another power, we multiply the exponents, t to the 8. Okay, let's not do this complicated way now. Let's get our derivative the way you'll probably actually get them all. All you'll do is you'll say, hey, I can use the power rule here. I've got a constant out front. So what happens is that the 8 comes down, so I'm going to do 16 times 8, and then write the t, and the 8 drops down 1 to 7. So my final answer would be 16 times 8, which is 128, t to the 7th. And to be totally honest, I've probably even done more work than you would do still, because you'd probably just go 8 times 16 is 128 and then t7. And that's great. You should get to that point. You don't want to be spending all this time doing this. But, I'm writing all this to hopefully understand the process. All right, last question. At what points on the hyperbola xy equals 12 is the tangent line parallel to the line 3x plus y equals 0? Okay, we're getting complicated here, but this is a really common sort of question you get in calculus. So we're talking about two things here. We have the hyperbola, and here's the formula of it. We like our formulas to have y isolated, and that's very easy to do, isn't it? We'd have y equals 12 divided by x. We want to know, when is the tangent line to this graph right here, when's it parallel to this line right there? Well, if we're talking about parallel, what do you know about parallel things that are parallel? What do you know about parallel lines? They have the same slope. So it sure would be useful to find the slope of this one right here. We can do that very easily. If we isolate y here, you get y equals negative 3x. This is in slope-intercept form. The y-intercept is 0, there's nothing there, and the slope is negative 3. So we know that this line has a slope of negative 3. We want to find the point on this hyperbola where the tangent line is parallel to that. How are we going to do that? Well, remember, when we find the derivative of something, what you're finding is the slope of the tangent line. So if we find the derivative of this right here, and then figure out for which x value does it has the same slope as this, negative 3, we'll have our answer. So let's work this through. First of all, I cannot just take the derivative of this right now, because I don't know how to do that. We'll figure out ways later. But even when we do it later, the easiest way to do this would actually use the power rule. And we can only use the power rule if we have 12x to the negative 1. Now it's very easy to use the power rule, right? Bring the negative 1 down and multiply by 12, so you get negative 12. Then you have x, and you drop the exponent by 1. So negative 1 goes down to negative 2. Why don't we write it the way we probably would? We'd have negative 12. This is a flip and negative, so it flips down to the bottom, and you get x squared. Okay, so we have a function now that tells us the slope of the tangent lines for every point on this hyperbola. So if you want to know what the point on the hyperbola that has an x value of 1, you'd put 1 in here, you'd have negative 12 divided by 1, you get negative 12. So when x equals 1, the tangent line to this hyperbola is negative 12. We don't want it to equal negative 12. We want it to equal negative 3. So what you're interested in is, when is it that this function right here, when is it equal to negative 3? So let's solve that. Why don't we multiply both sides by x squared here? If we multiply this side by x squared, then the x squareds cancel. So all we're left with is negative 12. What you do to one side, you got to do the other. So you have to multiply this side by x squared as well. So you get negative 3x squared. Next thing you probably do, divide both sides by negative 3. If you divide both sides by negative 3, you get 4 equals x squared. Last thing to do, take the square root of both sides. But you need to remember something. When you solve equations by taking square roots, you must put plus or minus. So your answer will be x equals plus or minus 2. So what are we looking for here? We're looking for at what points. So we have our two x values. The x values are 2 and negative 2, but we need some y values. How are we going to get them? Well, we're interested in the points on this hyperbola, so all we have to do is plug those points into this equation right here, or this one right here would be even better, this one right there. Either one works. So if I do it in the top one, 2 times what equals 12? 2 times 6 equals 12. If I do it for the second one, if I put negative 2 here, negative 2 times what equals 12? Negative 2 times negative 6. These are my points. So these are the 2 points on that hyperbola that have the same slope as this line, and that line has a slope of negative 3, so the slope of the tangent lines at 2, 6, and negative 2, negative 6 is also negative 3. Can you wrap your head around that? Pretty important. Okay, enjoy the power rule. You're going to use it a lot.